Hello, everybody. This is Team Data Nights, and welcome to our progress video. We'll be taking you through our progress on our project with CAMH, the Center for Addiction and Mental Health. We're working with them on sleep deprivation classification using bold fMRI data. Bold fMRI data is essentially blood oxygen level dependent data. Now, that highlights different areas of the brain depending on how much oxygen is present in the bloodstream there. And that can be quite useful for pulling out different features of the brain and understanding the state of what is happening at a particular time. We're using fMRI images that display this to support a classification. And the classification that we're looking to get is whether a subject is sleep deprived or whether they are not. And we have that information in a labeled data set of about 800 fMRI images, which we're looking to pre-process and feed through a classifier to see whether it's possible to make that classification or indeed whether it's not possible. So to start that, we've had to do a huge amount of pre-processing, and I'll take you through a little bit of that here. If we look at this Python file here, you can see that we've had to start masking our fMRI images. So the fMRI images exist across 4 dimensions. The 4th dimension is time, because the MRI scan occurs over several minutes. And then the first 3 dimensions are X, Y, and Z axes, so that it's a 3D image in space. Now, unfortunately, it comes in with a lot of extra information, such as the skull, which you can see kind of grayed out around here, as well as different parts of the brain which may not exist in some scans. So we want to abstract that all away, and the way to do that is to come up with a mask. So you can see that this is one slice in 2 dimensions of an image that has been masked. You can see that green outline there. Here's another example. It's quite similar. And here's another example. It's quite different. So looking at these 2 examples, then a problem starts to become apparent. These 2 masks are not the same, and when fed into a machine learning classifier, depending on how we extract features, they're going to end up being very different and not comparable. So what we have to do is we have to intersect all of these masks, and unfortunately, it's not as simple as calculating that off the get-go. We first have to resample every single fMRI image because they all have different properties. They were captured using different specifications. The major ones are affine, which controls the kind of spatial orientation of the image, as well as shape, which controls the physical resolution and dimensions of the image. So after quite a bit of work and quite a bit of computational power thrown at resampling all of these images, we've come up with a directly comparable kind of image. Now we need to intersect all the masks. And what that does is it calculates where a mask exists and where it doesn't, and it sets it to an intersection such that we get the same mask for every single image at the end of the day. Now we do lose some some data that way. I'll show you an example done with our first 5 tasks here. You can see that we're cutting off a little bit of the bottom here, and we're cutting off a little bit of the top, but the end goal is that this mask is identical across all fMRI images. So again, I'll show you an example with our first 5 images. You can see that we've neatly removed a lot of extra information which we don't need, which is just skull or various parts of the brain that we aren't interested in. And we have the exact same masked image across all of these different fMRI scans. This is just the first 5. We scaled this up and applied it to several hundred images in the data set, and we've come up with one shared masked image across everything. This image is, the dimensions are identical across everything, and we're ready to extract features and look further into it. So I'll pass it along to Tony to talk about the metadata extraction.
Thank you, Patrick. So essentially, the data that we're working with is scientific computing, neuroscience. The data is actually organized in what is called BIDS data structure, which is brain imaging data structure. Essentially, it's organized across a lot of different files. And all the fMRI and the metadata in different folders. And so we definitely, one of the main things, one of the main metadata we need to look at is something called confounds. Confounds is basically noise, things in the fMRI that are actually not related to the task at hand. For example, if the patient was moving, if the patient's heartbeat, which is rhythmic bold data. We definitely need to go through a linear regression to actually reduce all the noise there. So the next part we definitely want to do is grab all the images, of course, put that into a data frame, and also we want to go through the subjects, and there is a metadata file that has the subjects and their sleeping condition during a specific session. So there are 2 sessions that each subject is subject to, and one is sleep deprived, one is not. We definitely need to find which session the subject is sleep deprived. And we get basically through some code, we get this final data frame, which we see the subject, the session, the task, the path to the fMRI data, and whether or not they are actually sleep deprived during that time. So I'm going to pass on to Vis to talk about what kind of features we might be interested in extracting.
Thanks, Tony. So with that prelude said in terms of getting the data and pre-processing, and then looking at ways in which we can use the metadata, that leads us to the next point on how to convert this into a workable machine learning problem. And we have 2 broad approaches here to take. One is to convert this into a numerical problem and thereby use traditional machine learning methods to solve this problem. Or if you think about it in a different way, we have 3D brain images over time, and that presents us with an opportunity to convert them into videos and thereby pass them into neural networks and use neural networks to classify the videos. So if I may call your attention to this data frame over here, this is very similar to what Tony just showed. And as you can see, these are all the corresponding images, bold images of the subject and the session. These are passed through what's called a masking array. And the masking array, in short, just converts a 4D data into a 2D array, which is then can be used with traditional machine learning methods. So this is the kind of format we want to bring this to before we do any further processing. And some of the next steps that we will pursue will be to put these through some machine learning models and see what results we get. That said, let me pass it over to Alex.
Thanks, Vis. Just give me a second. Oh yeah, so just going off of what Vis was talking about, in the future, instead of also just looking at a per voxel basis, or like, well, then the 2D image will be just per pixel per se. We could look at different regions of the brain and see what kind of a time, analysis and signal we get. And of course, there's different regions of the brain, and there's different mappings of it. One mapping, for example, using the Harvard-Oxford one, provides 49 different regions of the brain, whereas other ones will provide less or even more, let's say. And if we could then generate a time series with a normalized signal for each of the different regions. So in this case, there'd be 49 different regions we can produce, and you can see a lot of the graphs are actually fairly similar. For example, like the different parts, subregions of the frontal gyrus have similar graphs, and this is confirmed with our correlation matrix here. As you can see, a lot of them are very similar because, well, a lot of these subregions are frankly right next to each other, right? So in the future, we could reduce this issue by using larger regions of the brain and generating the signal processing from it. Or we could actually just maybe even remove some of these regions directly using a correlation matrix. Another feature we could use is the connectome. So the connectome is just simply a mapping of the connections of the brain over a time series. So you can see here, some regions of the brain are more interlinked than other different regions of the brain over, for example, like an activity or the MRI. So using the connectome, we could also use it as a feature, and it may help us in the future for classifying sleep deprivation for our project. And that's it. Thank you.
Okay, thank you very much for attending our project update. If you have any questions, we're happy to answer them. Feel free to reach out to us by Moodle or email. Have a great day.